Great. So I'd like to thank Vinod and the other organizers for inviting me. It's really been a great event so far. And so this will be a two-part tutorial on secure multi-party computation. So just to prepare the audience for this, we usually use MPC to abbreviate multi-party computation, and somewhat oddly, we use MPC also as an abbreviation for secure multi-party computation. So if you feel uncomfortable about it, so do I. The only advantage of this over better acronyms like SMPC or secure MPC is that it puts you in a better legal situation in case your protocol turns out to have a bug. But otherwise, that's the acronym I'll be using, and most of the community uses. Okay, so as I said, the talk will have two parts. The first part, delivered by me, will give more of a cryptographic angle to secure multi-party computation. This is a very broad area, so certainly my part of the talk will be quite broad and less technical. I will have some technical parts, but it will be mostly an overview of the area. I'll start with a gentle introduction and some words about what we do in the area. Then I'll get into definitions, some examples for protocols, and I'll mention throughout the talk open problems, and also will tell you why we don't have a real risk of running out of them. So the second part of the talk will make the switch in the middle of the second hour. The second part of the talk delivered by Manoj will focus on the information theory angle. In crypto, we're kind of looking at big scale phenomena. We think of functions as having infeasible input domain most of the time, not all of the time. We deal with asymptotics, with computational complexity. In the information theory view, the main focus is on finite functions, and typically you consider many independent instances of a function. You consider the asymptotics when you want to compute the same small function many times. So this kind of puts the problem in a different regime. It's kind of like studying galaxies versus studying atoms. And of course, there are many points of overlap, but I think that the part of the talk delivered by Manoj will be very different in flavor than what I will talk about, not only in terms of the style of definitions, but also in terms of the style of the results. Okay, so let me start by answering the question, the teasing question that I posed before. Why are we never going to run out of open questions? You know, if you work on a very specific question in information theory or on some problem in combinatorial designs, you know, you run into the risk of the problem being solved and people moving on to study other problems. But for MPC, you know, it's such a general problem that really it captures almost everything you can think of that involves good guys trying to achieve something and bad guys trying to stand in the way. So you can think, for instance, of classical error correcting codes where the good guys are trying to communicate a message and the bad guys are trying to corrupt the encoded message. You can think of the whole area of distributed algorithms, problems like consensus, Byzantine agreement, and so on, as an instance of secure multi-party computation, again, given the type of broad definitions that I will cover. You can think of notions in complexity theory, such as interactive proof, PCPs, randomness extractors, traditional notions of complexity-based crypto, like encryption signatures, zero-knowledge proofs, that will be covered by Rachel later today. These are also instances of MPC, cutting-edge crypto primitives like obfuscation and functional encryption, and really, you know, the problem in its full generality gives you basically a language to capture almost every problem in the domains that I mentioned. So it's really too big to fail. If you don't like the area, you know, it will never fail, but government will bail it out. So it's here to stay. So when considering MPC, again, if you look at the list of special cases, you realize that some of them are not just about evaluating a function. You can consider reactive systems that involve a state that receive inputs and outputs in multiple rounds, but most of this talk will focus, as well as Manoj's part of the tutorial, will focus on the special case of secure function evaluation, where we have a function that has inputs and delivers outputs, and that's it, and that's the goal. The goal is to compute this function securely in a sense to be defined. Okay, and by the way, I'll be very happy to make this talk interactive, so at any point if you have questions or you would like me to expand on something, then please do interrupt me. Okay, so let me start by a motivating example. Suppose that I want to conduct a survey of how bad salaries are for academics in France. So I want to conduct it among the French people in the audience. How many people here come from France? Okay, not too many, so it might not be the best example,
no,
but
it's not public.
okay. Well, just your official income is public, right? I'm considering unofficial income as well. Good. So, right. So we have 6 French people. And the goal is to compute the average salary, or equivalently just the sum of the salaries, right? Since there are 6 of them, these 2 are equivalent in terms of information. And obviously, this is sensitive information, so they don't want to reveal anything about their individual salaries except for the sum of all salaries. So how do we do it, right? So one can think of many real-world solutions, but I guess that the most common one is to take someone everybody loves and trusts, discreetly tell him or send him via secure email the salaries. He computes the output and tells it to everyone. Okay, so this is a very good solution, assuming that everybody is willing to trust this trusted party. But the goal of secure multi-party computation is to achieve the same goal without a trusted party, to somehow distribute the trust between the parties. So here's a basic solution. By the way, for those who are not familiar with the problem, can you think of a simple solution? Okay, so here it is, probably the simplest example I can give here. Let's assume that we have some publicly known upper bound capital M on the sum of all salaries, right? So 10 to the 11 is safe. All the French people here, that's a safe upper bound, okay? I didn't mention the currency, by the way, but yeah, euros. Okay, and from here on, when I mention addition and subtraction, they're carried out modulo M. So the idea is to just start by having the first party pick some random residue R modulo M, right, a random number in ZM, and just mask her input by sending a message consisting of the input plus this random number modulo M to the second party. Right, this is a good idea because this is like a one-time pad. The second party from this message learns nothing about X1, the salary of the first party. And now we can continue deterministically by having each party just add his or her input to the message it received from the previous party. So we can just continue in a ring and go all the way back to the first party, who can now extract the sum of all inputs by just subtracting the initial randomness R from the last message it received. Okay, so this clearly produces the correct output. And intuitively, it should also hide the inputs because I explained it for the first message, but you can see that every message contains some partial sum of the inputs plus an independent random group element And we know that any fixed or any distribution of a group element, when you add a random group element, which is independent of the other thing, then you get something that's completely random, right? So it's clear here that every individual party, except perhaps the last one, gets something that's completely random. The message that it gets is completely random, right? And the last one, what it gets is a message that is just what it should be, conditioned on the initial randomness R. Okay, so you can think of your favorite intuitive definition of security. It is clear that this protocol reveals nothing but the sum to every individual party. But is this good enough? Can you think of any weakness of this protocol? Right, so if we, right, so this is the end. So if we look at the first two messages and we consider a collusion of the first and third party, then it is clear that together they can completely recover the second input, right? So if we take you know, the difference between the message received by the third party and the message sent by the first party, this is exactly the second input. And this is not something we should inevitably leak, right? We want to reveal the sum of all inputs, and this sum does not follow from the first and third. So given this sum, which we must reveal, and the first input and the third input, which the first and third party must learn, there is no reason to also reveal the second input. This information is not determined by the sum and the first and the third input, so this does intuitively this does illustrate a security concern or a security problem with this protocol in the case where the first and third party collude. And similarly, any two parties, if they collude, they can learn something which they should not ideally learn. Okay, so how do we fix this protocol to hide such additional information from any collusion of parties? Well, there is a simple solution of just using more messages. So consider this complete directed graph. So this is actually a tournament. So take a click and orient the edges arbitrarily. So we have n choose 2 edges. And now we assign to each edge a random group element which is picked by the source of the edge. Right, so R12 corresponds to a random group element which is picked by the first party. Okay, and what every party does is in the first round. Okay, so in the first round, the protocol will consist of 2 rounds of messages. In the first round, every party picks the random group elements assigned to him and sends it along the outgoing edges. Okay, so that every Rij is sent once in one message. And in the second round, every party announces his input plus the sum of all incoming messages, denoted by inbox I, minus the sum of all outgoing messages, denoted by outbox I. Okay, so you can easily see that if you add these messages, then because every random group element Rij appears in a single inbox and in a single outbox, this randomness cancels out and we are left with the sum of all inputs. And also it's a simple exercise. You can use, for instance, like simple linear algebra to show that every subset of parties learns nothing except their own inputs and the sum of all inputs. Okay, and this can be generalized using connectivity of a graph. So you can take any graph and you can prove that if you take a subset, this subset learns additional information if and only if it disconnects the underlying undirected graph. Okay, so this is a general claim you can prove easily using linear algebra. Okay, so this does seem to solve the problem. But should we be perfectly happy with this protocol? Like, do you think that it's a good protocol to run in general, or say for running general elections? You can also compute general elections by adding up 0-1 votes, for instance, right? Voting between two presidential candidates. Is this a good idea to run this protocol? What do you think? Anyone who is not familiar with this? Can you think of a vulnerability of this protocol? I just said that any subset learns nothing except what they should. Did I make any implicit assumption here? Okay, the implicit assumption I made, so in terms of what you want to learn, this is fine here in some sense. I will get into these definitions later, but certainly in terms of the effect you can have on the outcome, we're not happy with this protocol, right? For instance, any party can just pretend to have a completely random group element as an input and make the output completely random. Okay, so if we allow any ZM element as a salary, right? Even then, you know, salary, we want to compute the sum over the integers. So you know, getting the output modulo M is already not what this protocol is intended for. But if you consider goals like election, where you want every input to be restricted to be either 0 or 1, clearly this protocol does nothing to enforce such a restriction. So when we consider malicious parties that deviate from what the protocol tells them to do, we obviously need to do more, even when we want to compute something as simple as the sum of the inputs. Okay. So more generally, we have k parties that want to compute some function of the local inputs. We have a parameter t that specifies a threshold on the number of parties that can collude. We typically consider these parties as being corrupted by by a centralized adversary that can see everything these parties can see. And we want this central adversary to learn essentially nothing except the output of f. And we refer to this, again, still at the intuitive level, as a secure MPC protocol for f. So there are two basic questions that the entire community has been studying since the 1980s. First is, when is this at all possible? And second, how efficiently? And to answer this question, of course, we need most of this part of the talk, or much of it, will be about different ways of defining or specifying these questions. But very broadly, I can just classify. There are also multiple ways to classify results in the area, but we have one major classification is a distinction between the case where we do have an honest majority, namely this corruption threshold is less than half the number of parties. In this case, we can get a so-called information theoretic security, right, which is basically our way of saying that security holds against computationally unbounded adversaries. So in this case, we can securely compute every function assuming only secure point-to-point channels connecting the different parties. And if we don't have an honest majority, then we can either get computational security, namely security against computationally bounded adversaries. And this we can get, we need to rely, these results are unconditional. These type of results need to rely on unproven but widely believed cryptographic assumptions. And alternatively, if we still insist on information theoretic security, we can still get it even when there is no honest majority by assuming something beyond secure point-to-point channels. For instance, we can assume a so-called oblivious transfer. I will soon explain what it means, or a correlated randomness setup, which has also been a topic of some talks last week. What do I mean by oblivious transfer? So you can think of oblivious transfer as a two-party oracle. So it's a box that receives inputs from two parties. The party on the left is called the sender. It holds a pair of strings S0 and S1. And the party on the right is the receiver. it has a choice bit C, and this box delivers to the receiver the string selected by C. So the intuitive security guarantees are that the receiver does not learn anything about the unselected string. It can only learn one of the two strings. And the sender does not learn anything about the choice bit C. Okay, so this is a notion. I will use the abbreviation OT later in the talk. So this is kind of like a canonical atomic building block for secure MPC protocols in the case where there is no honest majority. Okay, so again, this is still very high level and informal. Yes?
So here, you always assume that the parties, I guess, what is it, dishonest but curious? I mean, in the sense that
right.
If I'm participating in a protocol, I can just send garbage into the
Yes, excellent question. So the answer is that essentially the same is true in both cases, but with minor variations, right? So in the case where the parties are malicious or the adversary is active, that's also another term for this. For instance, you have issues in both settings, and you need to say a bit more, and I will say a bit more later. But you can get results of this type in both the case of honest but curious parties and malicious parties. In the honest but curious case, if you write, if I stop the talk now and everybody comes up with a formal definition based on what I said so far, this definition will be consistent with the results. In the case of malicious parties, it's probably not going to be the case. Okay, what about efficiency? Again, this is an area that is the subject of a lot of research, both in the asymptotic or theory world and in the very concrete practical world. There are recently a lot of actual implementation efforts for MPC. And not only is it a fruitful topic of research, both for the crypto community and the information theory community, but also it's an area that is quite unusual in terms of how big the open questions are. So, you have many problems that look very innocent, and the gaps between upper bounds and lower bounds are huge, really almost as big as they can be. And unlike some other cases, for instance, in computational complexity theory, people are used to having these huge open problems, but in this area, there are usually good explanations or excuses, also known as barriers for why we're stuck. Here, for some of the central problems in the area, we have these huge gaps between upper and lower bounds, with no good explanations for why we're stuck or no good theory that unifies different open questions. So I think there is a lot of room here for better understanding, if not of the problems itself, at least of how they relate to each other and why we're stuck. Okay, and another thing I wanted to say is that, and this also relates to the more practical angle of implementing MPC. There are many areas in crypto where there is a huge, like a very big difference between solving a problem heuristically or coming up with a solution, an amateur coming up with a solution that the best experts cannot break, or an expert coming up with a very efficient solution that other experts cannot break. But in this area, especially in the information theoretic regime for MPC, it's really uncommon that we have a protocol that we believe it is secure in the sense that we don't know how to break it, yet we cannot prove its security. So again, this is quite different from the situation in other areas of crypto, including much of what Rachel will talk about. Right? I believe that. No, there's a lot we don't know, of course. But my point is that in many areas of crypto, including in zero knowledge, you can come up with protocols that we don't know how to break, yet we cannot reason about. And for information theoretic MPC, I mean, zero knowledge, again, as I said, is a special case of MPC, but certainly for information theoretic MPC, this is very uncommon. So that's a good thing, in a sense. Okay, good. So let me now get into definitions. And first, let me give you the general philosophy, which again is very broad. And if you follow this philosophy, you can formulate your own definitions, not only for problems in MPC, but also for problems in coding theory, like recent notions of non-malleable error-correcting codes or other types of error-correcting codes. And you know, this is known as the real ideal paradigm that can be, I guess, traced back to the seminal work of Goldwasser and Micali on probabilistic encryption, and then you know, pursued more generally in the work on zero knowledge and the first works on secure multi-party computation. And this real ideal paradigm basically says that if you want to define, first of all, it says that we're not trying to shoot for absolute security, but only for the best achievable security, right? Where in different contexts, this can mean different things. Then it says that we want to specify the best achievable security via some ideal process that we just postulate this ideal process to be the best we can hope for, right? So in the case of MPC, if you look at this solution involving a central trusted party, this is what we consider to be an ideal solution. We're not trying to do better than that, right? Of course, this ideal solution can also reveal information. In particular, the output is revealed. But this is what we define to be the ideal solution. So we're only trying to be as secure as this ideal solution. And then security says that whatever an adversary can achieve by attacking the real protocol, where the parties actually talk to each other and exchange messages, it could have also achieved by attacking an ideal protocol that employs a trusted party. Okay? So in my first example of computing the sum, achieve only refers to what the adversary can learn. And in this case, indeed, you can argue, at least for the second protocol that I showed, that every subset of parties, assuming everybody follows the protocol, every subset of parties can learn nothing from the messages they see except what is also learned in the ideal solution. But for crypto purposes, and again, in the next talk of Manoj, and I will also touch on it, you can come up with information theoretic, very natural information theoretic definitions, which generalize the definitions we've seen in Stefano's talk last week, or in other talks, definitions that involve definitions that refer to specific goals like secure communication. You can again get a definition that follows along these lines. But you know, a very useful concept in cryptography that kind of gives us a very crisp understanding of you know, how security is defined is this notion of a simulator. And this simulator is basically some interface that takes the ideal implementation and converts it in a sense into the real implementation. So it allows us to argue in a very simple way that the real implementation is in some sense equivalent to the ideal implementation, where the equivalence is established via this simulator. I will of course be more specific later. And this paradigm of using a simulator to capture the equivalence of the real and ideal implementations, it's actually captures as special cases both concerns like secrecy, what the adversary can learn, correctness, what influence the adversary can have on the outputs of uncorrupted parties, independence of inputs, right? That the inputs that, I mean, when the parties are malicious, they can, of course, pick whatever inputs they like. We cannot prevent me from lying about my salary. But still, you can hope that even if I lie about my salary, the salary I pick is independent of other salaries so that I cannot fix the sum to whatever I like. Right? So this is also captured because all these features exist in the ideal implementation. So the ideal implementation does give us secrecy to the extent possible, correctness and independence of inputs. So by equating the real world and this ideal implementation, we're automatically guaranteeing all these features that exist in the ideal implementation, but also what we get is better than the sum of these requirements. So if you try to formulate, and this has been done in the old days, especially for special tasks like voting protocols, so people had a list of requirements, you know, correctness, secrecy, independence of inputs, and so on. If you try to formalize a list of all desirable requirements you can think of, you will fall short of getting the actual definition that we get from this real ideal paradigm, because there are complex interactions between these different properties, right? So secrecy and correctness are somehow intertwined, especially when you have malicious parties. So the sum is that we get a very clean and strong definition that kind of subsumes ad hoc attempts to define different security features separately. Plus, it supports important features such as composition that I will mention soon. Okay, so let me get into more detail about how this real ideal paradigm works. So we have a real protocol. In the real protocol, we have parties talking to each other, but we can consider this protocol, this interaction. Yes?
By the last point, so what do you mean that if I prove secrecy, correctness, independence, and so forth one by one, separately, it cannot be that the protocol satisfies all of these simultaneously?
Yeah. Yeah, so if you prove, for instance, secrecy and correctness, it's kind of like if you have a pair of jointly distributed random variables, it's kind of like, you know, secrecy says that the first random variables are equally distributed. Correctness would say the second random variables. Of course, it doesn't mean that the joint distributions are. So there are security features that involve joint, for instance, you know, it might be the case that I cannot learn anything beyond I can in the ideal implementation. I cannot achieve anything, you know, any influence on your output that I cannot do. But if we consider what I learn and what I achieve simultaneously, then I can. So again, so this definition gives us an elegant way of basically saying that the real protocol is the same as the ideal protocol for every purpose. Okay, so in the real protocol, we have parties talking to each other. And we can consider this to be an interaction between the central adversary that corrupts a subset of the parties and the honest parties. And again, the adversary, I will talk about it later, but it can be passive. So this corresponds to the honest but curious setting. Or it can be active, which means that it can do whatever it likes. And in the ideal world, we have this trusted party that computes F. Everybody trusts trust this party, so it does compute F honestly. And the simulator, which is just a name for the adversary attacking this ideal implementation, it corrupts the same set of parties in the ideal world, but now all it can do, so now it has no messages. In the ideal world, there is no interaction between the parties. There is only this very simple, you can think of the ideal world as a very simple protocol in which everybody sends their input to the trusted party. The trusted party evaluates the function and sends back the output to every party. So here, if the simulator is passive, you know, if we consider the case of a passive or honest but curious adversary, then basically all the simulator does here is observe the output. Okay, that's all the simulator gains from this interaction. In the case of active or malicious adversary, the simulator can also pick his inputs that it hands to the trusted party, and it gets back the output. Okay, so these are the two. You can think of it as a complex protocol that involves direct interaction between the parties, and this very simple protocol involving an incorruptible party. Okay, and what we want, again, is that the adversary cannot achieve anything in the real world beyond what it could have also achieved in the ideal world. So for instance, if in the real world, as a result of this interaction, the adversary learns that the second input is bigger than 7, then we want it also to be the case that in the ideal world, the simulator, based on the output it receives, can tell that that x2 is bigger than 7, right? This is just an example. And if, this is for those who know who the guy in the left is. So anything that the adversary can achieve, if the adversary can bend the spoon after the real world interaction, then so can the simulator, right? Maybe F gives him the recipe of how this is done. Okay, but again, we do not only consider what the adversary learns, we also need to consider the effect of the adversary on the honest parties, and we do this by also considering the outputs of the honest parties. Right? We don't consider the messages viewed by the honest parties, but only the outputs of the honest parties, which captures the effect the adversary can have on these outputs. So what this simulation paradigm requires is that if you consider jointly what the adversary can see with the outputs of the honest parties, this is equivalent to what the simulator, and again, this will be made a bit more formal soon, but the simulator, he lives in this boring world. The simulator needs to come up with some transcript that emulates what the real adversary sees, right? So he needs to come up with the messages, and the local randomness that look like what the adversary sees in the ideal world. And the joint distribution of what the adversary can see and the output of the honest parties should be the same or roughly the same as the joint distribution of what the simulator produces and the output of the honest parties in this ideal experiment. Okay, so to make it more formal, we can consider, and we typically consider this external environment that is denoted by Z, whose goal is to distinguish between the real protocol execution and the ideal protocol. So the environment serves as a kind of a distinguisher that tries to, this is some guy, some hacker that claims, hey, I can break this protocol. And this is a skeptic that says, whatever you can do, I can do better. So whatever you can do by so-called breaking the protocol, I can do also by interacting with this ideal implementation. And the goal of the environment is basically to help this skeptic or help the adversary prove that he can do more. So for this purpose, the environment can pick the inputs to be given both to the adversary and to the honest parties. And it can observe the output or the view without loss of generality. The output of the adversary is the entire view of the adversary and only the output of the honest parties. In the real world, in the ideal world, it gets from the simulator his output, which emulates what the adversary can see in the real world, and it gets from the honest parties the actual outputs. And the goal of the environment is to distinguish between these two cases. So it outputs a bit 0 or 1, and if the probability of outputting 1 in the two games is noticeably different, then the protocol is insecure. It means that the real-world adversary, this hacker or parapsychologist, can do more than the skeptic. Okay, so we have, right, so here is finally some quantifiers here. So we say that the protocol pi is securely, so pi, a protocol is just a specification of how the parties can talk, right? So there is a next message function that tells you which message you should send given your input, your randomness, and messages you received so far. That's syntactically how we define a protocol pi. And the protocol pi securely realizes a function f if for every real-world adversary A, there is an ideal world adversary or simulator S, such that for every distinguishing environment Z, the probability of the real experiment outputting 1 is roughly the same as the probability of the ideal experiment outputting 1, where again, this real experiment and ideal experiment are as I described before. So environment picks inputs there is this interaction, you know, which is trivial in the ideal world, you know, and more complex in the ideal world, in the real world, and then the environment gets something from the real world adversary, again without loss of generality, whatever it observed in the protocol, and a message from the simulator that attempts to mimic what the adversary saw, plus it gets the outputs of the honest parties. So this is how the security definitions look like, and there is a major distinction between the so-called standalone MPC, where the role of the environment is restricted to picking the inputs in the beginning and collecting outputs in the end, and the so-called universally composable or UC MPC, where the environment acts as an interactive distinguisher and can send, while the protocol runs, it can send instructions to the adversary or the simulator, please do this, please do that. Okay, so for the purpose of this talk, we will mostly be concerned with the standalone case. Yes?
So you have this approximately equal to here, so let's say about two probability spaces.
Yeah.
In what sense are they, is this, we want an exact equality, or, you know?
Right, so I will now, in the time we have before the break, I will give you more than you want to know about different variants of this definition. But for now, this is just a single bit, right? So you can consider the perfect case where the probability of this bit being 1 is exactly the same, or you can consider some statistical case where this probability is roughly the same. But again, there's also a distinction between the case of a computationally bounded and unbounded distinguisher and so on.
I mean, I guess, you know, putting the information that we had on, right? I mean, there's a big difference between zero error capacity and having a lot of...
Sure. So we have both a perfect variant and a statistical variant and a computational variant. So let me talk about exactly addressing your question. Let me talk a bit about the landscape of definitions. So, yes.
So the quantifier also hides, you know, which set of parties are corrupted, right? I mean, when you say for every
Yes. So excellent. So when I say for every A, as Vinod pointed out, I did not specify who the adversary can corrupt, which set of parties the adversary can corrupt. So for every A should be for every admissible A, and one feature one feature we should specify is which set of parties the adversary can corrupt, and we also allow the simulator to corrupt the same set of parties. Okay, we actually, in a sense, require the simulator to corrupt the same set of parties by making the environment see which parties were corrupted. Yes?
Explain a little bit more about the simulator can see all the inputs of all the inputs as well as the output?
Only of the parties it corrupts, right? So the simulator, like the adversary, it corrupts a subset of the parties. It can see the inputs of corrupted parties and the output of corrupted parties. And in the case of active or malicious security, it can also determine the input sent to the functionality. Okay.
That's why you need an environment, because environment can see everything slightly more than the simulator.
The environment, it can see both whatever the adversary or simulator, you know, what they see in the protocol, or what the simulator pretends to see in the protocol, and what the honest parties actually output, which captures the effect on the outputs.
So can you think of environment as just a hypothesis test in the sense that it's really like 0 or 1, saying good or bad kind of?
So it's really about the difference between the probability of outputting 0, 1. So there is no significance to the actual probability. I mean, this is just, in the statistical case, you can think of statistical distance between this joint distribution and this joint distribution. Okay, so we have tons of different models, which you know, is not a good thing. We really should. I mean, in general, it's not good when there are too many variants of some problem. But the situation is not as bad as it seems, because most natural questions are only sensitive to very few aspects of the model. You know, again, for most of the questions, the big questions I will mention, you can come up at this point with your own formal definition. Again, what I wrote here is still quite high level, right? And the answers will be the same, even though different people here will come up with different exact definitions. We have general connections between models, so we have very elaborate web of connections that allow us to transform results from one model to another. And also we have a small number of standard models. So while there are many works on different on exotic models, there is a small number, you know, 2, 3 standard models in crypto that people mainly focus on. So having said that, let me just give you just the different axes in which definitions vary, or basically what it takes to precisely specify an MPC task. So first we need to specify what function we want to compute, and we typically use the slightly fancier name functionality to capture the fact that it's more than just a standard deterministic function. I'll refer to this later, but functionality, for instance, can also capture a reactive task, right? Just to give you one example. So something that takes inputs and outputs in multiple rounds. So you can think of a functionality as just an algorithm run by the trusted party. There is a network model which addresses, so functionality captures what we want to achieve. The network model basically says, how can we communicate? Do we have secure channels or not? OT channels, correlated randomness, and so on. There is the adversary, right? Who do we need to protect against? And there is security type, which says what type or what quality of protection do we want, say information theoretic versus computational. So again, I will not go over, you know, all the gory details, but let me just highlight some important distinctions between different flavors. So when we specify the functionality, what we want to achieve, again, this fully specifies the ideal model, right? It tells us what the trusted party does. And also we can view the functionality as telling us the inevitable vulnerabilities, right? What must inevitably be leaked? What type of influence the adversary must inevitably have on the output? Okay, we have a distinction between non-reactive functionality versus reactive. This talk I will focus, in the rest of this talk I will focus on the non-reactive case. There's a distinction between deterministic versus randomized, single output versus multiple outputs, right? In general, we can have a different output for every party and so on. Okay, we can also consider model leakage for those who attended Stefan's talk last week by taking some input from the adversary, say specifying some leakage function from a given class and delivering an output directly to the adversary regardless of which party is corrupted. And an important point is that the question which functionality is safe to compute is out of scope for MPC, and this is really what differential privacy is about, which will be a central theme later this week. So really that's a common misconception. MPC does not really tell you everything about building secure systems. It just tells you, you know, if you're happy with a solution involving a trusted party, then you should also be happy with an MPC solution in a case where you don't have any party you trust. Okay, sorry. I think that it's time for a break, or yeah, so I have some, okay.
So when you say more than this, right, you're saying if there's a solution to the second problem, namely which functions are safe to compute, you can put them together, you can use MPC to actually compute this function.
Sure, yeah. So even though they're orthogonal, there are also interesting interactions between the question of differential privacy and MPC. You can try to do things more efficiently, or there are many questions, you know, that combine differential privacy and MPC, or MPC can be applied for implementing a differentially private mechanism. But at their core, the two questions are orthogonal. Okay, so let's reconvene after the break.